and share the file.
Good afternoon. So today we will start the second part of this lecture series, that is on characterization techniques for advanced materials. So I am Dr. K.C. Barick. So I will take next 6 lecture on different characterization techniques that is necessary for advanced characterization of advanced materials. So if any query, you can contact me. My email ID is here. So before going to characterization techniques, so when you synthesize advanced material, so first thing is to study their material properties. So the material property is mainly defined on the two parameters. That one is structure, another is morphology. If you see this morphology and structure, and both you have to use by some characterization techniques. So you have to use these characterization techniques, different techniques to identify the different properties. So mainly, I will discuss that characterization techniques what we are going to study. So for advanced material, there are two type of study we require. One is structure, another is morphology or interface. When you come to the structure of the material, so the structure of the material we need two techniques. That one is mainly diffraction technique, another is scattering techniques. So in diffraction technique, we will cover mainly X-ray diffraction, electron diffraction, and Neutron diffraction. Whereas in scattering, we will mainly focus on X-ray scattering and Neutron scattering. In case of morphology or interface characterization, we'll see that XPS and X-ray photoelectron spectroscopy, X-ray absorption techniques, secondary and mass spectroscopy, as well as imaging technique of the SC, scanning electron microscope, and transmission electron microscopes. So this AFM and STM, that atomic force microscope or scanning electron microscope, so that I will try to cover if time permit. Otherwise, mainly I'll discuss other characterization techniques. So most of these characterization technique based on interaction of radiation, that is photon, electron, and neutron. So if you see the X-ray, all X-ray techniques is used to photon interaction. Whenever electron interaction, so you said electron microscope or electron diffraction patterns. In case of neutron, we'll see that how this interaction of matter with neutron, that's mainly with neutron diffraction, small angle neutron scatterings. So those things we will study. So mainly all these characterization technique based on two parameters, that interaction of matter with radiations. So now you're coming to, before going to radiation of matter, so we'll first discuss with interaction of light with matter. When light fall in matter, so there are three phenomena occurs. One is absorption, and second is scattering, and third is transmission. As you know, the absorption that interacts with the matter and completely absorbed by the depositing energy. But in case of this scattering, so you have interact as well as scattered, the refracted beam, it is scattered beam from the original direction, it deviates from the path. And there may be some energy loss or energy absorption occur. In case of transmission, it's interact and transmitted through the body, or it can be without loss of energy or with loss of energy. You can see in this diagram that the photon interaction H nu is coming, and then different types of electron cell scattering techniques is arranging. So all these three phenomena occurs in case of light interact with matter. So when light interacts with matter, there is a phenomena occur called attenuation. The attenuation is nothing but scattered plus absorbed. So whatever the incident light, that can be considered as a combination of scattering and absorption will be the attenuation factor. You can see this example when you have 100% energy is falling on a material, and then if there is transmission efficiency 90%, you can see only 90% is transmitted and 10% absorbed. And each step is getting that 10% is getting absorbed. The fourth cycle you can getting 66% transmitted energy. So overall, if you see the intensity of the light that finally coming out of this pore or that cycle of absorption, that the attenuation factor I, that will depend on I0 into e to the power minus mu x. That mu is your fractional linear transmission coefficient. So here it's mainly on the depends upon the transmission coefficient, how much energy will be attenuated during this step. Similar to light, when radiation, that photon, electron, or neutron that interact with matter, so different phenomena also occurs. So in case of interact, that you can see this interaction is mainly it doesn't obey any law. It's a chance of law of chance that depends. So in this case, when photon is generally have few interactions and exponentially attenuated, and photon interaction are expressed in terms of cross sections. But whereas in case of electron, experience large number of interactions, and then that it will lose energy during the process of the electron interaction, and expressed in terms of electron range as well as material, how the material stopping power of the electron. That's it. But in case of neutron, being a small size comparative to the whole nucleus, and it has a that's why it has a very low probability of interactions. So these three phenomena occurs that you can see here, that you have a neutron, you have X-rays and electrons, that it can interact with the atom as a whole or nucleus itself whole, or it can be interact with the tightly bound inner electrons, or it's loosely bound outer shell electrons. So at the same time, it can interact with the extranuclear space surrounding the nucleus. So you can see here, so when you have a light that falling on neutron falling onto the material, it can two paths. One is nuclear scattering. Otherwise, it can have a magnetic. Since neutron has a magnetic moment that interact with other magnetic material, you can get a magnetic scatterings. In case of X-ray, you have electromagnetic scattering. At the same time, you have X-ray scattering that takes place here. But if you have electron, you have electron interaction, that electron interact with the material for the other electron, as well as electron scattering takes place. So these are the three phenomena that occurs. Now you coming to the interaction of X-rays with matter. We'll discuss broadly on this. You see, when X-ray hit a specimen, the interaction can be radial various signals or emission or effects. You can see you have a specimen here. On the specimen, when you have X-ray light incidence, X-ray radiation falls, you can see there may be first phenomenon of absorption, that heat. Some of the X-ray can get absorbed, the material that generate heat. And the same time, so you can able to get some fluorescent X-rays can produce, or the same X-ray beam can be scattered in different direction. If the scattering is occurs, then you have a two phenomena occurs. One is coherent scattering, and another is incoherent scattering, that is Compton scattering. In case of electron, it can generate also electrons. That will be photoelectrons can be possible one case, another case can be Compton electron, or that X-ray can be transmitted directly without any interactions. So mainly that X-ray can also be refracted or reflected at very small and very low angle, that X-ray can be refracted and reflected. But major phenomena is the scattering and fluorescent X-ray generation, as well as some electrons will be generated as well as transmission beam occurs. So when you come to the coherent scattering, that is that I discussed that the X-ray scatters that from bound charges, that coherent scattering. So when energy of an incoming X-ray photon is substantially less, very low energy of the X-ray than the binding energy of the electron, in that case, radiation undergo a change in direction without changing wavelength. There is no change in wavelength. It will simply interact, and there will be a change in direction occurs. There will no electron will be ejected in this case, and there no energy transfer. Since it's a very low energy, so there will be no energy transfer, no ionization process occurs. You can see the photon incident here, lambda 1, it falls on the material and interact with the lambda 2 here, and you can see both lambda 1, lambda 2, they have similar wavelength. There will be no change in this case, and no electron is getting ejected. So those coherent scattering will not contribute anything related to phase information or any material information. Instead, it will give you thermal diffusion scattering, that is scattering due to some defects in the material. That type of scattering you will able to see, or air scattering can be occurs. So this interaction mainly occurs when you have energy of 15 to 30 keV, very low energy, you can see coherent scattering. But when you have incoherent scattering, that is Compton scattering, that occurs when incident beam is deflected from original path. You can see here that incident beam is coming here, and after for interacting here, this material, its direction is changing here, and that electron is moving in some other direction, that material is moving. So here that X-ray photon is deflected from original pathway, and with the interacting with electron, and the electron ejected from the orbital, and the X-ray, because of the interaction, it may lose some energy and travel certain distance. That electron can travel certain distance. The energy change here depend upon the angle of scattering, but the angle at which the scattering occur, that this angle, it depends on the angle of scattering. This X-ray theta is the angle of scattering instead of the nature of the material. The scattering X-ray photon has less energy, it's has longer wavelength, and it's a lesser penetrating, that incident photons. So here that you can see here, so if you see here that collision kinetics, that's mainly based on that conversion of the energy and momentum. That the P that what is the kinetic energy PE, that will be h nu of the incident photon and depend upon the scattered photon h nu dash. So h nu minus h nu dash will be decided. And here no fixed phase relation between incident and scattered wave, and it's directly proportional to the electron density. Of a high Z material, your scattering will be higher. That sigma, the cross sectional for electron, that no Z dependency, sigma is dependent to the Z due to free electron assumption, and directly it's electron depends on electron density. But when you have a photoelectron, that energy of high, when the incident photon eject an electron, you can see here that incident photon is coming here and falling on the material electron, and that electron is coming out. That photoelectron of K cell is coming out. So in this process, one electron is that incident X-ray is removing one electron from the K cell. So in this process, it's called photoelectric effect, and it is known as photon electron interaction. In this case, when the electron moves from the one energy state to vacuum, so you have created vacancy is created. So that a vacancy exists due to the removal of electron, and thus one or more characteristic X-ray. Whatever the X-ray is coming here, depending upon whether it is K alpha or whether it is L cell is K beta, so all or K gamma. So depending upon all those parameters, so you'll be able to see how proton and electron interacts. And other reluctance process occurs in this case is fluorescence can be occur because of that some X-ray can be radiated as a fluorescence, otherwise you can see the Auger electron. So that we'll discuss when we talk about X-ray photoelectron spectroscopy. So here mainly you can see the photoelectron energy of the photoelectron will be equal to the energy of the incident photons minus binding energy of the electron. You can see that the electron inside this electron has some binding energy with this nucleus. So it has to overcome that binding energy, the electron to knock out. So the photoelectron energy will be equal to incident and photon minus that energy of the binding energy. So photoelectric effect is predominant for low energy photons, but higher binding energy than that of electron. It has low energy, but the binding energy of the electron has to overcome. Then you can able to eject out one electrons. So it is higher atomic number Z materials like this, you can get more photoelectron effect. So its probability of interaction is proportional to Z to the power 4 by E to the power 3, that energy. So it is the relation where it depends. So in addition to those Compton effect as well as photoelectric effect, third phenomena occurs is pair production. So pair production generally occurs whenever high energy photon passes near a another atomic nucleus. You can see that incident photon is here, and you have an atomic nucleus is situated here. So when you have high energy photon coming out, and that photon converted into two particles here, electron minus or electron plus, that is positron and electron, you will get two separate entity. So to create this positron electron, the two particles require minimum energy is equal to 1.202 MeV. You need minimum energy that the excess energy of the photon is given to the particle as a kinetic energy. So minimum energy requirement is 1.02. You have excess energy that you have. So that energy will be converted into the kinetic energy of these two materials, two entities. So these then undergo a typical charge particle interaction and losing some energy each interaction. So since you have an electron and a positron, so they may interact, and you have a charge particle interaction in this case. So here pair production occurs in the field of nucleus, that is Coulombic interaction. Due to Coulombic interaction, and the interaction cross section varies proportionally Z square. In case of Compton, that's directly proportional to Z, but mostly directly proportional. But in case of pair production, you have a Z square relation. You can see the three phenomena that for low energy you have a photoelectric effect that predominates. In case of Compton transferring occurs in all energy, but in the middle, and if you see the water, how this water interacting with the different energy of electrons, you can see at low energy you have a photoelectric effect, and at high energy you have a pair production, and in between you have a Compton effect you will be able to see. So pair production generally will occur when you have an energy is more than 1.02 mega electron volt. And this curve, the interactive curve, you can see here what is the curve you are seeing here. So these curves, the nature is almost similar, but in case of depending on the material, there will be slightly, dominates which factor will dominate, whether photoelectric dominate or pair production dominate, that depends. But most over the interaction will be, the nature will be like this. So other than this interaction, there is another interaction called photodisintegration occurs that's quite high energy, whenever 8 MeV electron. In that case, that the photo degradation, disintegration occurs. So threshold energy is 8 MeV for all nuclides, with two exceptions, that deuterium is 2.2 and beryllium is at 1.6 MeV. Other than this, in all other cases, that minimum energy required is 8 mega electron volts. So it's a direct interaction of energetic photons and observed nucleus. So in this case, the nucleus emits a photon, that is gamma, or more likely a neutron, that gamma n, that you can be able to get in photo disintegration process. So now we'll discuss that the interaction of electrons with matter. So how electrons interact with neutrons. You can see here that the electron is negatively charged and a rest mass of 9.1 × 10 to the power minus 31 kg and a charge of 1.6 × 10 to the power minus 19 coulomb. It's a spherical electron act as electron act as both particle as well as wave, that we know de Broglie wave equation. So how electron act as both particles and wave. So wave electron beam can be coherent as well as can be incoherent. So you can see if a coherent wave, then you can see that all the phase are in same, all the phase are matching the same position. But incoherent, so different wavelengths of the phase. So that in that case, so that some sort of you can say incoherent waves will be formed. So when you have a material, on the material you fall the electron beam. So like X-ray, so different interaction here occurs. One is you can create that same electron can be returned back, that is backscattered electrons, or that electron can be absorbed and knock out another electron, that is called secondary electrons, or it can produce a characteristic X-rays as well as some inelastic scattering or elastic scattering takes place, or electron can be directly transmitted without interacting with the material. At the same time, you can get a secondary electron, that is the Auger electron you can form. So mainly when like X-ray, when electron interacts with the material, you are able to get produce additional electron like the secondary electrons or Auger electrons, or the electron can be bounced back. So mainly that interaction of electron with material takes place, that elastic collision of electron if you see. So there will be no energy transfer. You can see here is the atom, then the electron is coming here and it deviates its paths. So without losing any energy. So that is elastic collision of the electron. So electron penetrating into the electron cloud of an atom is attracted by Coulombic force, that positive potential nucleus has a positive potential. Because of that, electron will be attracted towards it, and that path you can change its path. So that will be, in that case, since there is no energy loss, it will be elastic collisions. So elastic interaction deflects the electron beam along its new trajectory, causing a spread in lateral. You can see if that electron beam, depending upon the charge, that Coulombic interaction, it deviates the path. You can see the incident electron is coming here. So here in this is the backscattered electron almost return back, and you have a angle theta, which is scattered electrons. So depending upon the interaction, so different types of scattered electron or backscattered electron will be formed. So the closer the electron comes to the nucleus, the higher is the scattering angle. You can see, so when it comes very closer, so there is a probability of a backscattered electron. A strong elastic scatter very near to the nucleus may result in a beam that completely return back, that is called backscattered electron. You can see that electron beam is coming back mostly, so it's called backscattered electrons. Similarly, the probability of elastic scattering will depend upon the atomic number, that is Z square. The heavier the atom, the stronger is the positive charge of the nucleus, so interaction will be quite high, and that decreases such energy increases. That interaction that is proportional to 1 by E square here. So in case of inelastic collision, but there is a energy transport between the incident beam, and then you have a energy getting transfer. You can see that initial energy, there is a W loss is there. So this energy loss happens gradually, while the distance travels from the atom. It is dominated energy loss mechanism of electron. The inelastic collision is the main phenomena where electron loses energy upon interaction with the matter. And interaction produce excitation can be occurs. It can be, there can be ionization of the material. So both can be possible in case of a inelastic collision. And this inelastic collision will produce mainly, as I discussed, that one is a secondary electron it can generate. It can generate photons. That light, it can generate an X-ray. So X-ray can be produced during this X-ray, characteristic X-ray, or it can produce also Auger electrons. So when you have an incident beam, so that electron will be diffused and it will knock out an electron, that is secondary electron. If that deviates the path, that will be the backscattered electron that we discussed. And high energy electron of incident beam removes electron from the inner create a hole. And this hole that it will be filled from the higher orbitals. There's a hole up in the inner shell can be filled up the electron from the outer shell, giving away another electron that causing either it can be a X-ray or it can produce a electron. When you have a hole here, so that hole will be filled from an electron from the outer orbital. This electron, if you have, it can jump here. So you can from this the excess energy that will come out as that X-ray characteristic X-ray, or it can be that another electron will be because of this that can eject another electron from the higher orbital. So that will cause electron. So that we'll discuss later. So in addition to this inelastic collision, you have a background interaction. That background interaction is mainly Bremsstrahlung emission. So electron emit Bremsstrahlung due to the acceleration caused by the electrostatic field of atom. When electron passes through the material, so because of that energy, it can interact with different material, so energy will be slowly lost. So that will give a background radiation. So the emission that will call Bremsstrahlung radiation. In Bremsstrahlung event, electron with high energy generate photons of low wavelength W. So then you have a low photon will be produced and you can get a background radiation. In addition to that, positron annihilation is also occur. That positron penetrating to a medium can annihilate with electron, like the pair production when you have a produced positron and electron. In the positron annihilation, that positron can interact with the electron to form, two photons collide, and you can get a photon. You will get occur when electric energy, the kinetic energy of the positron is larger than the absorption energy. In that case, annihilation takes place. So in that the positive and E minus they will annihilate, and you will able to get positron annihilation spectroscopy. Say based on that techniques. So overall, the electron beam when interact with a material, it depends upon the interaction volume. So interaction volume you can see here. So this is a material. On that material you can see this shaded area. So here this is the main area where electron beam is interacting. So electron beam once comes, if you go on random interaction with when inside the material, it will able to get a where generate a volume up to that volume that interaction is maximum. So both elastic and elastic scattering together distribute in a single incident electron beam over a three-dimensional 3D region that is called interaction volume. And this interaction volume can be simply described as a thing called electron range, up to what path length electron can move. So that can be also termed as the electron range. So the electron range is the simply a value that is useful for rough comparison and scaling various signal distribution. We want to see how the electron signal is distributed inside this area, inside this volume. So that will decides by this electron range parameter. And size and the shape of the interaction volume depends upon the nature of the elastic and inelastic beam. So that we'll see here. You can see whenever interaction volume mainly depends on electron energy, atomic number, and density of material. So how dense is the material, how much energy you are providing to the electron, as well as the atomic number, the jet of the material. So you can see incident beam or low kV have a low energy, so there is probability that incident beam can interact with here you can see low volume, that the interaction volume. You can see here the interaction volume is like this. When we have a low kV, there is a possibility that interaction either penetrating, if penetrating high, then you will be able to see the low energy. You can see this type of surface interaction. And low jet material, that this is case of low jet material, it's in low energy. So low jet material, the penetration is high. In case of high jet material, the penetration is less. You can see here. But in high energy, you can see that interaction volume is quite high in both low jet and high jet. So overall, the electron range, that radius of the hemisphere, if you see, this is the radius of hemisphere. So that hemisphere radius will depend upon jet factor and or the electron density and the energy you are providing that. So specimen is assumed to be a flat when this phenomena is occur and the electron upward. So then only tilt angle at the particular angle it's falling. So you can be able to find out how the energy of the electron is interacting to the material. You can see here you have an electron beam coming here, and the top surface that is in this area, you can see that mostly we produce electron, that the surface phenomena occurs to 100 nanometer scale length here. So in that range, you can able to see mainly secondary electrons. And then you have a little deeper. Then if you go in here, so 500 micron up to 500 micron, you can able to see how the backscattered, electron is coming out. So mostly, and then if you go little deeper, you will able to see X-ray that use your choromluminescence, and even less than that, Webster, the continuous X-ray that background radiation will come if you go keep on going inside. So here the electron beam falling, so you are able to generate, from surface phenomena as well as, little different type of electron is coming out based on that different characterization. Like the secondary electron, Webster electron, they will be used, in case of scanning electron microscope, or the transmitted electron is coming out here that from this interaction that will use when transmitted electron microscope. Or even there are some, when the electron beam is coming here, that energy may be, decreased during the interaction. You will be able to get, say, electron energy loss spectroscopy, yield spectroscopy, and as well as, different diffraction phenomena that occurs, you can able to see, and you can see the composition analysis using EDAX analysis. Or you can have the electron spectroscopy you can do. So that we'll discuss individually when we'll come into the lecture. So as I discussed that backscattered electron, that's electron beam coming from the top surface, it's directly interacting with the material that is very close to the nucleus, and you're able to that electron is getting back. That is called backscattered electron. And that backscattered electron coefficient N backscatter will depend upon the number of electron beam incident, that NB on the specimen divided by number of backscatter electron generated, NBAC. So that depend on the coefficient that is of the backscatter electron. So backscatter electron backscattering increases monotomically as atomic number Z increases. So it's mainly used for atom number contrast feature. You can able to see when contrasting imaging, then in ACM, that case you will able to see backscatter electrons. But in case of angular distribution, that you can see when it increases, when theta, that depends on the topographic contrast mainly used. So tilt angle, this is the phi. So how the electron beam is coming at this surface directly at 0 degree, this is tilt angle, then increasing the tilt angle, you will able to see different, backscatter electron density can varies. So maximum at the normal to the surface, so directly normal to the surface, then you're able to see that maximum, backscattered electron generation. So similarly, in case of secondary electron, that the secondary electron has loosely bound outer cell electron, that incoming electron will get absorbed and it will knock out another electron from the core level. So that will, come out as a secondary electron. So here that mostly loosely bound outer cell electrons of the specimen that will come out as secondary electron. In that case, what happened, that kinetic energy of the incoming electron is so high, so it has to overcome the binding energy of the second electron to knock out. So here similarly, secondary and coefficient depend upon these two parameters, number of secondary electron and number of total electron injected on the system. And then one secondary electron can generate another secondary electron, that low energy, that Sc2. So that secondary electron can able to generate a third secondary electron. So similarly, it can be possible to more number of secondary electron productions. So here the emission of secondary electron is very sensitive to the condition of the surface, because low kinetic energy severely limit the range of secondary electron. For secondary electron generation, you need say high energy, high kinetic energy electrons. If you have a low kinetic energy, then it's difficult to generate secondary electron. In that case, it depends upon the surface of the material. So mainly that tilt angle, if you increase in this case, the secondary electron generation will decrease. So here you can see that if the angle will decrease, so in that case, if you come down here, the secondary electron will less. In this case, the secondary electron is quite high, you'll be able to produce. So similarly, like X-ray and electrons, so we have neutron also interact with matter. So coming to the neutron, as you know, neutron was discovered by that Chadwick. In 1935, he won the Nobel Prize. So you can see a barium atom here that then you can observe a helium-2, which are 4 molecular weight. So it can create a carbon-12 as well as one neutron will be produced. So this neutron that produced, so that has a mass of 1.67 10 to the minus 27 kg. That is more than 2,000 times more than the electrons. And it has as I told, that it has a magnetic moment of 1.9 mu m. So nuclear magnetic. So nucleus, since a magnetic moment, they interact with the material. Both this that magnetic interaction is possible in addition to the nuclear interactions. In this case, you can see the properties of neutron. If you see the neutron as electrically neutral, they have a high penetration, deeper penetration because of no charge. They're electrically neutral, and it can be the wavelength is equivalent to Armstrong wavelength. In this case, energy of million volts can show a motion. You can able to, since you have a wavelength is quite low and the energy of the electron is million volt, you have a both structure and dynamic, both phenomena, both properties you can study using neutron. So this is the neutrons, that depending upon the energy, they are also divided into mainly three types. The one is thermal neutron, that is slow neutrons. You can see here energy less than 0.5 electron volt. In case of intermediate energy is between 0.5 to 10 keV, whereas fast neutron energy is quite high, that's greater than 10 keV. So it's all like electron neutron interaction of follows both particle as well as wave characters. So that so mainly the neutron is produced source of neutron, if you see. So you can produce neutron in a research reactor by a chain reaction. You can see it's a spontaneous fission reaction. You have a nuclear uranium-235 nucleus here, and when a neutron absorbs, so that will be split into two nuclei, and then you can able to continue this process. In each step you will get 2 to 3 neutrons, and that neutron will further scale of this reaction. It's a common chain reaction. The continuous flow of one neutron per fission you will able to minimum you will able to get, and that is one method. By research reactor you can produce neutron, and similarly by spallation source by incident H plus ion that can be absorbed by the material, high jet material, and you can able to get more number of 10 to 30 neutron in each absorption you can able to get. So here it's an accelerator driven process where photon can be, that H plus ion can be absorbed by the material, spallation of nuclear reaction, nuclear process occurs. But if you see the brightness or fluxes of neutron X-ray sources, you can see in case of neutron, you can able to see that brightness is quite low, 10 to the power 15 order. But in case of the X-rays is quite high, rotating around 10 to the power 16. But these two are mainly, these three is mainly based on that this high energy X-ray sources where you will able to get quite high 10 to the power 26, 10 to the power 33 order of brightness. So depending upon this flux value, that different that a neutron or X-ray can be used for different characterization techniques. So neutron flux is much slower. So that's why when you go for a neutron analysis, neutron spectrum, neutron diffraction study, you have to go for a longer time required for measurement. Then only you'll able to get a better features of the material. Otherwise, in case of X-ray, that you can achieve with a lesser time because of that intensity of the flux. In case of X-ray, is quite high. These are synchrotron-based technique. So in case of synchrotron, you can able to get quite high brightness. So that if you see that neutron interact with the materials in mainly different types of processes occur. One is that elastic scattering, that the neutron will, there will be no energy loss, nothing. In elastic scattering, you can produce another neutron, or there is absorption or capture is possible, or fission reaction can be possible. And these are the three phenomena that can be occur. So since neutron has no charge, it interact with matter and can high penetration depth. You can see it pass closer to the nucleus, and nucleus radius very close, can go very close to the nucleus. And because of smaller size nucleus of relation to the atom, neutron have very low probability of interactions, and it can travel quite longer distance, but interaction probability is very low, and it can interact with electron both magnetically as well as normal interaction. So you can see here, if you see neutron has high penetration depth, and that when neutron is absorbed by a matter, it go to the unstable excited state, and then it can elastic scattering, it can just let's say interaction will come out same in neutron, or it can be resonant elastic scattering, or inelastic scattering left in excited state, and or it can produce a radiative capture, that is see gamma ray can be produced, or it can produce proton, deuterium, or doubly charged helium. So production of charged particle can be possible in case of neutron absorption, or that after observing excited state, that unstable nucleus can break down to two nuclei and you have some additional neutron. That is called fission process is possible in this case. So you can see the neutron capture, if you see, so neutron captured by the nucleus by absorbing material. So that the incoming electron will absorb by, you can see sodium-23 metal, you have a slow neutron. So that neutron is coming to this and it's absorbed, you will get a sodium-24 and it's a gamma ray emission. So when the formed compound is unstable, thus emit either N gamma, N electron, N alpha, or N proton, you can able to generate in this process. When compound nuclei emit only gamma ray, we call it radiative capture. But when you have a, other case that in electron, neutron, the charged particle can also produce. And probability of capture is inversely proportional to the energy of the neutron. So you have a low energy neutron, probability of capture is high in that case. So you can see some example of neutron capture. Neutron with hydrogen, it can produce that this is deuterium with one gamma emission radiative capture. It can cadmium can absorb similarly, or boron, or in nitrogen. So these are different neutron capture reaction you can see. So where that this technique is used for different applications like neutron dosimetry or shielding, that in case of hydrogen, in case of this boron, boron capture, boron neutron therapy we use in case of boron. So different application you can use. You can see similarly that fission can also occur, that uranium-235 can absorb one neutron, a fission product 2-3, the 2-3 neutron that will be available for more further reaction. So mean number of neutron released in a fission process is 2.5, that is critical mass, which is to retain a chain reaction. If energy exceeds a critical mass of fission, then nuclear freeze. So any neutron can, fission process can't occur with the absorption of the neutron. So beyond a critical mass, that critical mass, that energy, that critical energy of fission, the nuclei will split, you're able to get, further two additional nuclei. So in addition to that, that interaction, those neutron capture or breakdown of fission occurs slow neutron, interaction of slow neutron. If you have a fast neutron, you have able to see this type of elastic scattering, that is energy less than 10 MeV. That in that case, the neutron with particle that interact in such mass is such a high, it behaves like a billiard ball type of interaction, and material is like hydrogen, like water, wax, concrete. With them, when high energy neutron interacts, so that interaction is approximately billiard type interaction, and after collide with nucleus, neutron deflected its different direction with losing some energy, and that energy loss is a recoil that produces recoiling of the nucleus. So you can see the energy recoiling nucleus absorbed medium. So you have a recoiling nucleus and some neutron will be emitted in that case. But since it's in that case, the total energy is conserved in this process. So recoil nuclei quickly become an ion pair and loosely through excitation, lose energy through excitation process or ionization process occurs. This is the most important mechanism when neutron damage tissue. In our body tissue, if you see some neutron fall, so those are mainly hydrogenous material. So that cause some tissue damage because of these first neutron interactions. So in addition to that elastic, you have also inelastic interaction is possible. Neutron interact with the particle much greater mass, that is iron or some heavier metal, steel. In that case, the interaction is inelastic. So it's analog to the ping pong ball striking a foul ball. You can see two heavy mass there. The heavy mass interact, a small mass interact with heavy mass. In that case, energy transfer to the target nucleus and neutron is re-emitted with lesser energy. You can see that incoming electron will transfer its energy, and it will be that the emitted neutron has less energy than the incoming neutron, and it produces some gamma ray. So total energy in this case is not conserved. So in this case, energy of the neutron after collision will be dependent upon this E equal to E0 initial minus what the gamma radiation occurs. Then inelastic scattering occurs predominantly when you have a high jet materials. So no significant tissue dependent, that no interaction will occur because of first neutron, no significant from tissue dose point. But this type of inelastic scattering occurs when you have a the energy is transferred from the neutron to the system. We'll see here. So the thermal neutron, when neutron, a very fast neutron is coming here, like 1 MeV energy. So interact with the first nucleus, and then its energy lose some energy, and then it go to another interaction, lose another set of energy. And like this process, the energy loss process occurs. And finally, when energy in the range of 0.25, so neutron will be captured. So slow neutron with high energy electron, you can see the energy is continuously losing, and whenever going down, so neutron capture occurs. So fast neutron, then slow down to thermal neutron, and then the capture process occurs. If you see the probability interaction, I told neutron, very small, tiny molecule compared to the nucleus, so probability interaction is very less. So that, we express in term of Bahn, that you need to express the Newton cross section, that 1 Bahn is equal to 10 to the power minus 24 centimeters square. You can see number of scattered Newton per second by number of incident electron flux, that will be the probability of interaction. So what is the number of neutron, scattered to the probability of total neutron when flux is coming. So depend on the nuclei as well as nuclear energy. That the neutron energy as well as the nucleus of the material, both it depends upon both the parameter, and total cross section is Newton, how much Newton is scattered, how much Newton is captured, and how much involved in the fission. That is the total cross section we'll be able to get. And both in macroscopic scale, it should be n0 into sigma total, that n0 is, that's Avogadro numbers, that in a cubic centimeter area. To increase the interaction probability, if you want to neutron interaction with particle, you increase the probability of reaction, you need some moderating, or you have by use which you have to slow down the velocity of the neutron, then it will have to interact with scatter wave. So generally that's why the graphites and heavy water are used as a moderator in case of neutron interaction. So neutron loses energy as they interact with matter, and the beam intensity drops continuously as it propagates to the materials. And slowly from high energy, when you go down to the lower, then neutron captures. So if in the beam intensity, if you see, that is expressed in terms of attenuation length, like light absorption, here I equal to I0 e to the minus mu x, and mu that you can express it that scattering length Bj. So that depends upon the isotope and the dependent of Q vector, that I will discuss later. So mainly the macroscopic cross section is used for neutron in place of linear mass absorption. In case of light, we use mass absorption or linear absorption coefficient. But in case of this neutron case, we have used macroscopic cross section is used at I equal to I0 to the power minus mu x. So it's characterized by mainly by attenuation length, that mu, that will decide how the interaction will take place. So we'll just take 1 or 2 minute break, and then we'll start the second part of this, that on X-ray So far what I have discussed is, how does that define that X-rays, neutron and electron interact with the matter. So that we have seen that X-ray, that photons and electron, and that mainly, that the X-ray interaction, nuclear interaction, or some electron interaction occurs in this process. And, based on those interactions, so we will discuss different characterization techniques. So first we will come to the X-ray and its properties. Before going into the X-ray characterization techniques, we'll discuss which X-ray and its properties depending upon the interaction of X-rays with matter. If you see X-ray, so it was discovered in 1895 by German physicist, Röntgen, William Röntgen, that during cathode ray experiments. So he discovered that X-ray, since that X stands for unknown matter, at that time he was not able to identify what this radiation, so he termed it as an X-ray. So this could be that mainly due to that penetration of what substance, the black and white he see. So when Röntgen observed a new type of radiation, possibly due to the interaction of electron with the glass wall of the tube, that time he suggested that it could be detected by a side of the tube that is. So this X-ray is mainly could penetrate opaque substances, like that time we observed that Blackian or photographic film and produce a fluorescence or ionization of a gas. So that he termed as X-ray. So X-ray is defined as a weightless package of pure energy with no electrical charges and travel in a wave along its straight line with specific frequency and speed. So it doesn't have a electrical charge, and it travel in a mostly straight line. You see that X-ray can have both physical as chemical, biological, or physicochemical characteristics. You can see that X-ray has mostly the wavelength in the range of 10 to the power minus 9 to 10 to the power minus 11, and that of was a very shorter wavelength, and it is a very high energy. That X-ray, if you see in the electromagnetic spectrum. So, coming to the physical properties of X-ray, X-rays belongs to a family of electromagnetic radiation. They are electromagnetic radiation having wavelength of 10 angstrom to 0.01 angstrom. So, it's travel at a speed of light in vacuum, and that is almost 186,000 miles per second. And these are invisible to eyes, so we are not able to see those X-rays. So, they cannot reflected. They can't refract it, they can deflect it by magnetic or electric field, and they don't possess any charge. Since they don't have any charge, they can be deflected by this electric or magnetic field. They are pure energy with no mass and transfer of energy in the form of quanta that is called photons. So it has no mass, and they can penetrate various objects. The degree of penetration depends upon the quality of the X-ray intensity as well as the beam. So depending on the beam intensity as well as wavelength of the X-ray, you can able to find out how the penetration depth of the X-ray. As well as it also depends on the material on which it penetrates, in addition to these two factors. So if you see the chemical and biological properties, X-ray induced color change of several materials. When you have a materials, some chemicals that do on that the X-ray falls, it will many changes occur. For example, methyl blue get bleached. So green apple green color, sodium plantinocyanide turns into dark greens. So depending upon the interaction, the different colors can be produced. So X-ray destroys fermenting powder of enzyme. So enzyme that you call fermentation process, so that X-ray can destroy that power. X-ray affect also photographic papers as well as films in the same way as visible lights. So X-ray excites both biological material, which enable them to part in chemical process. So some of the materials which are not excitable biological materials, so those things can be excited by the X-ray process. It can also cause biological damage. X-ray can cause damage of body tissue. So they are transmitted through healthy body tissue but absorbed by the bones. So makes X-ray used for medical diagnosis. So X-ray, in case of biological application, we use it in a medical diagnosis because soft tissue of our body, so where X-ray can penetrate easily, whereas you have a bone material, so there X-ray will not pass through. You're able to get this photographic film on depending upon the X-ray attenuation. So these X-rays are produced by the conversion of kinetic energy of the electron into electromagnetic radiation. So for the production of X-ray, first you need an electron source. So from the electrons, so high energy electron, that will be converted into the electromagnetic radiation, that is nothing but X-ray. You can see here, you have a X-ray tube here, then the X-ray tube, you have a copper anode, this black one, this is copper anode, and the copper anode, your tip, you have a tungsten target, the tungsten is the and you have a filament here. On the filament, you have access high voltage you apply. Because of high voltage, some electron will generate here. So those electrons will fall on the tungsten target, from where many X-rays will come out. So X-rays are mainly produced by striking of high energy electron beam on the target material, that is mostly used tungsten. And this X-ray provides an environment for production of X-ray. So X-ray tube, that this is the X-ray tube that we hear. So that X-ray tube provides the environment. So it has an evacuated envelope. Inside that we produce X-ray. So X-ray tubes mainly require, as we discussed, the first one is electron source. That electron source has to be there for generation of X-ray. Then electron acceleration potential. So you have to convert low energy, that electron to high energy. But you have to accelerate it, you need a potential barrier there. And then target X-ray generation. That is the tungsten source that we use to target. So those type of target material. So major component, that is a cathode, that is electron source composed of filament, low resistance tungsten wires. Or you have an anode, that is accelerating potential. Anode is a target electrode and it's maintained a positive potential, so that that it can go through the positive towards X-ray, migrate to X-ray. Then you have a rotor or starter targeting device. You have to, depending upon the angle and all this, you have a rotator or a metal envelope you need. You can see here, this is the metal envelope that is there, inside which the X-rays are generally produced. So electrons are released from the cathode, are accelerated towards the anode by electric potential difference between and the kinetic energy. So the electron which are produced from this, so they will migrate to this cathode. During the migration process, what will happen? So you have a high electrical potential difference there, so that it can attain a high energy. Once that high kinetic energy is generated here with the electron, so when then it fall on the anode, the energy loss of the electron takes place, and that energy is captured or is created an excitation process where X-ray can be produced from this source. So along with the X-ray, since it is a high energy thing, so some heat can be produced also. So intensity of the electron beam decides the intensity of the X-ray beam. So what is that incident electron beam mainly decides the X radiation, intensity of the X radiation. If you see, 99% of the kinetic energy converted to heat, only 0.5 to 1% electron energy is converted to X-ray. So most of the kinetic energy will be transferred to the heat during this process X-ray generation. And this heat is mainly generated because of this, you can see. So when that you have a target material, those positive electrons are coming, and then it's interacting with the different target atoms. So there is a multi-interaction process occurs in this case. So the positive electron released from the cathode interact with the outer shell of the electron, the target atom, but don't transfer energy for the ionization of the outer cells. So outer cell electron simply raised to an excited state. So the outer cell electron immediately, after some unstable state, it can immediately drop back to the normal energy levels. So emission of some infrared radiations. So this constant excitation and return of outer cell process is responsible for the heat. So once that electron is coming here, that electron is excites the inner electron. So it go to the excited state, and after some time again it bounces back to the unstable state. It go back to the same energy level. During this process, it's some energy will be lost. So that energy is mainly in the form of infrared radiation. That IR radiation produce heat in case of X-ray. So in addition to that heat, so we also able to generate some characteristic X-ray. So characteristic X-ray are the main thing that used for X-ray diffraction analysis or any small scattering X-ray scattering techniques. So X-ray produced two things mainly. One is background radiation, that is Bremsstrahlung radiation. Another one is characteristic X-ray radiations. So the projected electron interact with the inner shell of the electron of the target atoms, and each electron in the target atom has a particular binding energy. You can see, so these are the electrons different levels. So these electrons are, situated in different energy levels with a particular binding energy. With the nucleus, they have a particular binding energy. So to overcome this binding this electron with the kinetic energy of the incoming X-rays would be much higher than the binding energy of this particular electron. So when the electron of high energy, totally remove the inner shell electron, so there will be a vacancy will generate. So unfilled shell energetically unstable. So this vacancy will be generated. So here to that vacancy, so you have to, outer shell electron with less binding energy from here to here or from here to here. So outer shell electron will fall into this process to fill this inner orbital. So in this process, some energy, excess energy that will be lost in terms of a characteristic X-ray. So characteristic X-ray is produced with an energy equal to the difference between the binding energy of the electron cells. So, this K cell electron is bound in a particular energy, L cell is bound with a particular energy. So that the difference between this K cell L cell binding energy when there is a jumping from higher to the inner orbital, so the excess energy that will be termed as a common X-ray, characteristic X-ray. And this characteristic X-ray is unique to a given element. So each element has a different characteristic X-ray. For example, if it's a K cell, in case of tungsten, you can see the binding energy is 69.2, L cell 12.2. So depending upon this binding energy, that we have a different X-ray will be produced. So the target material used in X-ray tube include mostly high-jet material, that is tungsten, or in rhodium, this type of material used, or molybdenum we use in the X-ray source. And as the energy of the incident electron increases above a threshold energy, then characteristic X-ray production occurs. And percentage of characteristic X-ray, increases depending upon that how the energy of the incident electrons. So mainly, so depending on the binding energy of the material, so different material has a different characteristic X-ray. You can see here. So where you have a variety of energy transition occurs, between adjacent cell material. So you can see this slide. So you have a K cell electron, and from L cell, the X-ray will produce from K cell, the migration of K orbital electron, then termed as a K alpha. So from here, you will be able to see the K alpha or L alpha or N gamma. So depending on the K, L, or M cell, we are able to generate different, alpha, these radiations. So you can see, so variety of transition occurs between adjacent atom alpha and non-adjacent beta cells in the atom. You can see here. So there is a transition between K alpha 1, K alpha 2. So you can see they have different binding energy. In case of K alpha of tungsten is 59.2, K alpha 2 is 57, K beta is higher 67. So within each cell, other than K cell, there is a discrete energy subcells which results in fine energy splitting of the characteristic X-ray. Like the characteristic X-ray, other than those generated from K cell transition, are unimportant as they're almost entirely attenuated. Like mostly the K cell electron we use for the characteristic X-ray radiation we use for different diffraction or scattering experiment. The higher energy, that Ki beta or K gamma, those we are not considering. So mainly that if you see here that you have a K alpha, K beta, you are able to generate. So for K alpha, you can able to generate that when you have a K cell electron transition, that in case of K alpha or K beta, the higher energy, that you can see that in for an X-ray with copper target if you use. So copper target, that K alpha and K alpha 2 and K beta is possible. That K beta is sometimes create noise or some, in the X-ray diffraction pattern. So K beta we use to remove the splitting of the peaks you can observe. So K beta is to remove by using Newton nickel filter, because nickel filter has absorption is equal to that of energy of that K alpha energy, K beta energy of that copper, so that that can so completely absorb the K beta, even able to get only K alpha. In this case, you can see some of the filter here. So for case of copper, you can see nickel filter, that is Z-1. You use copper, the atomic number 1 minus is nickel. Similarly, molybdenum, zirconium, in cobalt, it will be Fe. So you can use different type of that filters depending upon the target material. So it's a wavelength is generally, if you see that that kilovolt we are applying, that 120 12,400 by voltage we applied, and it depends. The X-ray production is mainly depend upon the that Mosley law wavelength mu whenever C into Z minus sigma. So they see the Z, the characteristic of the material that decides which X-ray we can get. In addition to the this particular this X-ray, you're able to see the with addition to the characteristic X-ray, you're able to see some X-ray fluorescence. So X-ray fluorescence, you can see that some of the material, like for example, if you have done some X-ray of iron oxide, Fe3O4, you can, in case of copper target, you're able to see that quite large number, in the background radiation. So the background intensity is quite high. So noise you will able to get. So that's because that copper, in case of Fe, it generates some fluorescence material, strong fluorescence of this chromium, vanadium, titan. So signal will come. So depending upon that, some different of fluorescence, spectroscopy are designed depending upon this X-ray fluorescence coming out. Some atom absorb incident X-rays and fluoresce then them as X-rays. So that this incoming X-ray that it will absorb that once some X-ray which you copper K alpha that you are producing on the iron system, so that X-ray will absorb and it will emit as a fluorescence. So absorption of X-ray decreases the diffracted signal. So because of that, you will get lots of background noise. So the increase in background noise from fluorescence of the X-ray can be removed by if you use a proper diffracted beam monochromator. You are using different monochromator, you can reduce that fluorescence signals, or there is a particular energy sensitive detector you can use, and that detector can be able to produce that capable to control that fluorescence signals. So in addition to the characteristic signal that I told, that some background radiation comes. That background radiation we call it as a Bremsstrahlm radiation, and this Bremsstrahlm radiation produced by the projectile electron interaction with the nucleus of the target material. So when a projectile electron completely avoids the orbital electron and pass by the target nucleus, it slow down or change its course by reducing its kinetic energy. You can see the 3 electron incidence is coming here. Number one is going to then scattering back, mostly impact, highly impact with the nucleus, maximum energy, and the other two, like two shorter distance interact, and third is quite long, far distance from the nucleus. And depending upon the close interaction or distant interaction, you will able to produce that X-ray with the maximum energy, low energy, or moderate energy. And this loss of kinetic energy during this process, what is happened that interaction that kinetic energy getting reduced, and this loss of kinetic energy appears as X-ray and is called as a slow down radiation or Bremsstrahlm radiation. That energy is quite low as compared to the characteristic X-ray. So distance between the projectile electron and the targeted nucleus determine the amount of kinetic energy loss. So that how far is the nucleus to the projectile electron, that decides the kinetic energy loss. A direct impact of the electron, target nucleus results maximum, that I told, that maximum energy will be produced when we have a direct interaction with these atoms. So if you see that the Bremsstrahlm interaction, you can see this is the background radiation, and this background radiation you have a range of energy from continuous spectrum you'll able to get. In this continuous spectrum, you'll get characteristic X-ray K alpha, K beta will come like this, but this background radiation is mainly due to the kinetic energy loss during the interaction process. X-ray of low energy with much greater abundance. Low energy, have a greater abundance of high this type of background radiation. So average X-ray energy is about one third to one half of the highest. You can see the highest energy you can see here 90 is here. So maximum you can able to see here around one half, around 40, 45, or this one third. They are the maximum background radiation you will be able to get. So X-ray production efficiency, that is the intensity, is influenced by the target atomic number and kinetic energy of the incident. So mainly that if you see the kinetic energy of the X-ray, that will decide how that loss process occur of the kinetic energy decide the X-ray the background radiation. So in case of X-ray, we are able to generate two type of mainly things. One is crystalline X-ray, that is used for diffraction or techniques or any scattering technique used for characterization process. Another is background radiation, that will be Bremsstrahlung radiation, that will only provide background to the systems. So these X-rays are mainly used for different purpose. One is for security purpose, one is for medical reasons purpose, one is analytical purpose. In case of security, we use in cargo or airport for checking of baggage scanning. In case of medical, that X-ray used for radiography. You can different you can see able to see the fracture and all those things by using medical X-ray. In case of analytical techniques, that X-ray used for X-ray electron, X-ray photoelectron spectroscopy, XPS, X-ray fluorescence spectroscopy, XRF, X-ray diffraction technique, XRD. In case of XRF, again, wavelength dispersive spectroscopy, energy dispersive spectroscopy. So those type of X-ray techniques are used to analyze the materials in case of this. So here in the case of today's lecture, mainly we discuss with how the X-rays, neutrons, and electrons interact with the matter. You can see here that X-ray wavelength is quite low. Okay, 1 angstrom, neutron is almost 1 angstrom. So in that energy will be X-ray is quite high, 10 to the 4 electron volt, whereas neutron is much lower, 0.08 electron is 0.50 electron volt. So mainly interact with electron, with that X-rays, and is penetrating, highly penetrating, but interacting with the nuclei, the neutron, it has a much higher penetration because of that, don't have a charge, and then interact with the electron, it's a less penetrating in this curve. So the electron is mostly interact with the electrons, but it's a very less penetrating. And you can see here the X-ray, there were two phenomena that mainly I assume the absorption phenomena, that X-ray incident will fall on the material, it will absorb. Another is scattering phenomena. And depending upon the scattering, we'll be able to see the X-ray diffraction or X-ray scattering techniques. In X-ray absorption, we will discuss the X-ray absorption spectroscopy. In case of electron also, that we will be able to produce backscattered electron, we will be able to produce secondary electrons, X-rays, Auger electrons, that we will discuss the SEM, TEM, and other characterization techniques. In case of neutron, the neutron beam with a high energy that will not interact with the low energy. You can see that absorption or scattering or capturing of the neutron occurs, and then that will able to produce different neutron interaction, disintegration processes. So they depend on that. Two techniques we'll discuss: the neutron scattering as well as the neutron diffraction that we'll study. In next class, we'll mainly focus on the the first part of the system, that is X-ray diffraction techniques, its principle and its instrumentation as well as its application in some sample analysis. Thank you. If any questions, you can raise. The time is here. If there is no question, then we'll meet day after tomorrow on the second lecture. That will be on the X-ray technique, X-ray diffraction techniques, this instrumentation, and application in different analysis. Thank you.